So in my last class, I talked about a problem, combinatorial problem that was known as instant insanity. And in that class, I have shown how this problem can be solved easily by using a very simple graph theoretic technique, basically graphs, edge disjoint subgraphs, etc. So that was one of the applications that we have already seen in my last classes. In today's class, I'm again going to talk about very practical things that has a lot of implications as well as applications in real life. So today I'm going to talk about mostly walks, paths, and circuits. So as I mentioned in my earlier classes that I'm going to follow the book by Norsing Deo. So this is from his book directly. You can see that this is section 2.4 and the heading is walks, paths, and circuits. So the question is, what is a walk? So intuitively, we can see that walk means as usual. Suppose in graph theory, we should have some vertices uh, and some edges. Now, what does it mean this walk? Suppose these are the, so you can travel through this. There is no need to write a straight line. So if I write like this, then also it stands for an edge. If I have a straight line like this, then also it has an edge. That means the connectivity is more important. So to this vertex, this edge is incident at this vertex and this edge is incident at this vertex. And suppose there is another edge from here to here and maybe from here to here. Okay. So what is the meaning of an walk? Okay, so let us just directly read out from this definition. A walk is defined as a finite alternating sequence of vertices and edges, beginning and ending with vertices, such that each edge is incident with vertices preceding and following it. So what does it mean? Suppose this is the vertex, say V1, say this is the vertex V2, sorry, this is the vertex V2, say there is maybe a loop here, and this is the vertex V3, which is the vertex V4, and say V5. So there are 5 vertices, and say the edges are labeled like this: E1, maybe I can, yes, E1, then the loop is say E2, E, sorry, this is E3, E3, then E4, then E5, and E6. Okay, so there are 6 edges. So the walk is nothing but, as it mentioned, is an alternating sequence of vertices and edges. So it means that it should be an alternating sequence. Say the starts with V1, a vertex. It may start with any vertices, say V1, then there must be some edge. So from V1, I have only one option, that is E1. Okay. Then from V2, it goes to V2. So it's an alternating sequence. So first vertex, then edge, then again vertex. So then it should be the turn of an edge. So I have many options. Like from here, from V2, I may take V6, I may take V2, I may take V3, or I may take V5. So any one of them. Say I have taken V3, sorry, E3. I have taken, say, E3. That means this one. Then I reach to V3. Okay. So you may stop it here. Now you can see that this is an alternating sequence. It starts with V1, then edge, then V, then edge, then V. So now if you go back to this definition, it says that a walk is defined as a finite alternating sequence of vertices and edges beginning and ending with vertices. So you can see that we starts with a vertex, we end at a vertex, such that each edge is incident with the vertices preceding and following it. So each edge, there must be some vertex at the beginning and at the end. So it's incident with an vertex preceding and after it. And it should start from a vertex and end to some vertex. And it's an alternating sequence of vertices and edges. So that's a example of a work. So this is an example of a work. Okay. So you may have some bigger work. For example, you may start from vertex V5, then say E6, then you must go to V2, then you may take E2, then you may again come to V2, and then you may go to E3, you may come to V3, then you may go to E4, then you may come to V4, and maybe you can stop it here, or you may go to E5 and then uh, V2, and you may stop it here. Now you can see that there are repeated occurrence of these vertices V2. So V2 occurred many times. But note that none of the edges they occurred more than once. So V6 exactly one, E2, E3, uh, then E4, E5, all the edges they appear exactly once. Okay. So according to this book, the definition of work here, they mention that no edge appears is covered or traversed more than once in a work. So here that means in the definition they have included this property that no edge should repeat more than once. Okay, but in many other authors they actually called work means any sequence of alternating vertices and edge starting with a vertex ending with a vertex. So many of the authors they allow repetition of the edges, and they distinguish work and they give another name which we call trail. So trail means where you have this along with extra condition that no edge will repeat there more than once. Okay, that means in this book work is actually same as trail for other books. So in since I am following this book, so I will prefer work as an alternating sequence where you cannot have the repetition of edges. So just it's a note that some of the authors they use this term as trail. So they define work as just an alternating sequence of vertices and edges where the edge may be repeated, but in trail they don't allow to edge to be repeated. But in this book the work and trail are the same. Okay, so in my lecture I will assume that this work means here you don't have any repetition of edge, but note that you have repetition of vertices. So the vertices, the repetition of vertices are allowed here in the definition of work. Okay, okay. So a vertex, however, may appear more than once. So there is some example. I am skipping that example. So this is some images. Uh, okay. So a work is also referred to as an edge train or chain. So he has given some extra term of the work, that is edge train or chain, and many other authors they uh, write it as trail, as I mentioned earlier. The set of vertices and edges constituting a given work in a graph is clearly a subgraph of G. See, suppose this is an example of a whole graph. So this is the whole graph. And suppose you consider an alternating sequence. For example, V1, V1A, V2. Maybe I can just copy it. Okay. So if I have this, then you can see that. So this is the whole graph G. So this is the whole graph G. Now you can see that. So this is maybe considered as an walk, say V1, then A, then V2, then V3, V2, then B, then V3, then C. So it comes here again, then again it comes to V3, then D, and then V4, and you may stop it here. So it starts with some vertex V1 and ends at vertex V4 with some alternating sequence of edges where no edge repeats more than once. Okay. Now, if you consider this, so this is nothing but if I write it like this, so this one, and then I go to V2 and V2 to B, I have taken this one, and then I go to come to V3, and then I again have a loop here. I again come to V3, and then I have taken D, and I stop it here. So this is nothing but it starts with V1, then A, then V2, then B, then I have V3, then I have a loop which is C, and then I come to V4, which is nothing but my D. Okay, so this is, you can see that this is nothing but a subgraph of whole G. So I can consider this to be S. S is again a graph, and this graph is nothing but a subgraph of G. So now the statement, I think it's clear to all of you that it says that uh, the set of vertices and edges constituting a given work is a graph in a graph G is clearly a subgraph of G. Now I think it's clear. Okay. So few terms. So vertices with which a work begins and ends are called the terminal vertices, and they are called terminal vertices. So if I consider this as my work, then these two vertices which starts and ends, so these two vertices are called terminal vertices. Okay. So V1 in that particular example. Okay, it is possible for a work to begin and end at the same vertex. Such a work is called closed work. So it may happen that an work starts and ends within same vertex. For example, if I consider this, if I consider my work like this, I come here, I go through here, I come here, I go back to here. So you can understand that V2 is my terminal vertices, and it is the starting vertex as well as it is the end vertex. So in that case, we call this work to be a closed work. Now just try to remember the problem that we mentioned in our first class, that's Königsberg bridge problem. Now try to understand or try to relate the definitions that are defined here with that basic problem that we had, the practical real life problem that we mentioned earlier. So there we had the Königsberg bridge problem. There also we faced the similar kind of situation. So now you can understand that these basic definitions are actually leading to some specific direction, which actually will able to solve or will try to solve the given practical problem. So now you can understand what is the definition of a closed work. That means if you have a work that should start from a particular vertex and that should also end to that particular vertex. That means the initial and the terminal vertices must be the same. So that is known as closed work. A work that is not closed, that is the terminal vertices are distinct, is called an open work. So now you understand what do you mean by then open work. Now another very important term is there that is known as path. So what is the meaning of a path? So here you can see that in my examples here, few vertices we repeated, right? Here we don't have any repetition, but I think the example was inside this, just at the background of this image. So if I remove that one, then you will able to see the whole image. Maybe I can go back to, if it allows. Okay, let's see. Oh, it's not possible because it has some buffering. So I cannot go back to that by Control Z. So maybe 50 or 60 step I can go back, but it cannot allow me to go maybe 70 or 80 steps back. Okay, anyway, So we had, for example, for this image, if I see that, so here, suppose I have taken a walk from here to this, say V1 to this, then say this, and then say this, and then say this, and then this. Okay. So I started with this and I end up at this. But you see that if I write it like this, then I start with, say, V1, then A, then V2, then B, then V3, then C, then again V3, then D, then V4, then H, then V5. Okay. So it starts with V1. So they are the initial vertices. So this is nothing but an example of a walk. But here, note that it's a particular kind of work where these vertices V3, it actually appeared twice. So if you put some extra condition, not only the edges, if the vertices should not repeat more than once, then there is some special name. Okay. So an open work in which no vertex appears more than once is called a path. So till now we talked about open work, work, closed work. Now it's an open work in which no vertex appears more than once is called a path, or simply, or a simple path, or an elementary path. So it's mostly with this name path, it's more common to all of us. So it's basically path, where this is nothing but a work or a trail in which no vertices repeats more than once. Okay, that means all the vertices must be distinct. So you can understand from the definition what is that path. In other words, a path does not intersect itself. If it intersects with itself, then there must be a loop. So that means you have to repeat the same vertex. But in a path, in an open path or in a path or elementary path, you cannot allow this. The number of edges in a path is called the length of a path. The number of edges in the path is called the length of the path. So now you can see that if I consider this, so this is not a path. So this is an walk, this is a walk, but not a path, but not a path. Okay. But I can have this. For example, if I consider, say, V1, then A, then V2, then B, instead of taking this loop, if I avoid that loop, then if I directly go to D, sorry, V3, and then directly go to D, and then V4, and then H, and then V5. So you can see that here neither edge nor the vertices, they appear more than once. As a result, this is an example of a path which starts from some vertices and which ends up at some vertices. So it's an open work, and it never has some the property that it will not repeat any of the vertices more than once. So this is an example of a path. And so you can understand what is the length of the path, the number of edges that appeared here. So here, number of edges, first A appeared here, then B appeared here, then D appeared here, then H appeared here. So the length of this path is 4. So 1, 2, 3, and 4. So the length of this path is 4. So I think the idea of length of a path is clear to all of you. Okay. So it immediately follows that then the edge which is not a self loop is a path of length 1. That means an edge. For example, it might happen two things. As I mentioned, either it should be like this, or there are two vertices on which there is an edge. So if I consider an edge like this, then so if I have a path like this, then must be the length must be 1. Okay. So that is, it immediately follows that an edge which is not a self loop is a path of length 1. It should also be noted that a self loop can be included in a work but not in a path. So as I mentioned, self loop here we have included the self loop, this one, which was included in a work but not in the path. So we avoided that path, aborted that self loop to just to stop repeating the vertex V3. That's why this is a path and this is a work which is not a path. Okay. The terminal vertices of a path are of degree 1 and the rest of the vertices called the intermediate vertices are of degree 2. Now you can understand, if you have a path, if you consider a path, okay, like this, then the terminal vertices must be of degree 1, but all the intermediate vertices, the degree is 2. Now you may think that, okay, the degree here, intermediate degree is 1, 2, 3 and 4, but why it's saying 2? So when we are considering a path means it must be a subgraph of the original graph. So when we are considering the degree of the internal vertices, we are not considering the whole graph. That means here we are only considering this part. For this path, we are only considering this subgraph and not the whole graph. Now it will be clear to you that this is an intermediate vertex, this is an intermediate vertex, this is an intermediate vertex, and they are, these two vertices are the terminal vertices. So the in the subgraph, though it looks 2 in the original graph, the degree of this vertex in the original graph is 2, but in the subgraph, which is referred as the path, the terminal vertices has degree 1 and each of the intermediate vertices, it must have the degree 2. Okay, now it's clear, I guess. So this degree, it says that this degree, of course, is counted only with respect to the edges included in the path and not the entire graph in which the path may be contained, as I mentioned. So a closed work, now we talked about the openness, like open path and all. Now I am talking about a closed work, that means whose initial and the terminal vertices are the same. A closed work in which no vertex except for the initial and the final vertex appears more than once is called a circuit. So this is again an important term. So this is known as circuit. That means here no edge will repeat, no vertex will repeat except for the initial and the terminal vertices. That means it's a closed work. For example, so there are few examples given here. So you can understand this. So here it starts with this, maybe here one, this, and it again come back to here. As a result, this initial and the terminal vertices are the same, and you can see that no edge repeats more than one. As a result, this is an example of a circuit. Here also you can see that this is one circuit. So self loop is again a one circuit. Okay. So now these definitions are clear to all of you, I guess. Okay. So circuits are sometimes also called cycles. Mostly it's known as circuit. Sometimes many of the authors, they also call it cycle or elementary cycle, circular path or polygon. Okay. So they are in, if you till now whatever I mentioned, you can think in that way. So basically a subgraph, any collection of edges in G. Okay, so that is the subgraph. Then from that subgraph, if the edge does not intersect, that means if you don't have repetition of edge, then we call it what? For many other authors, they mention it as trail. Now this work does have two parts. One is the closed one, another one is the open one. So if this is a path, that means if it's an open one, that means not intersecting open work in G, that means no edge should intersect with each other. That means no vertex will repeat with each other. Terminal vertices are different. So here no repetition of edge, no repetition of vertices. and the initial vertex and the terminal vertices are different, then we call it as path. And if the initial vertex and the terminal vertices are the same, then we call it as circuit. Okay. So till now, whatever we did, it's basically the basic idea of this. Okay. So till now, any question? Any question that you have? Okay, fine. So now we are going to describe another very important concept that is known as connectedness of a graph. What do you mean by a connected graph? So intuitively, you all understand that what is the meaning of a connected graph. Let me try to explain. So suppose we have few vertices, say this vertex, and suppose I have a graph like this, and suppose this. Okay. Now, so there are, say, V1, V2, V3, V4, V5, and V6. Now tell me whether this graph is connected or not. Somebody please tell me whether
Sir,
this
not
graph.
connected.
Very good. So this is not connected. So now you have all have some intuitive idea what is the connectivity of a graph. What do you mean by a connectivity of a graph? Now can somebody be try to explain using the edges and vertices what should be the definition of connectedness of a graph? So you all have some intuitive idea. Now try to explain this thing. So that's very important for mathematicians. That's very important. We may have some intuitive idea, but we should explain in terms of mathematics in a formal way. Okay, so somebody can you please try?
Uh,
So
sir, sir,
yes,
the definition can be given any two vertices, Vi and Vj, if there exists a path from Vi to Vj, then the graph is connected.
very good. So as he mentioned, according to him, he says that take any two vertices, say original graph is say V and E, where V is the collection of all vertices and E is the collection of all edges. Take any two vertices, say Vi and Vj. If you can find, take, so here any two arbitrary vertices. Okay. Now the graph is said to be connected if you can find some of the path which starts from say V1 and which ends at Vj. So it could be any arbitrary vertices. So very good. So now you understand what is the definition. Take any two vertices. If there exists a path from Vi to Vj, then we call it G as a connected graph. Okay. Now, if it is a disconnected graph, then you can understand that there must exist some of the vertex such that there exists no path from some of other vertex. Okay. So it's any two vertices, then that means there exist two, at least two vertices Vi and Vj such that there exists no path between Vi and Vj. If that happens, then we call it as a disconnected graph. So you can understand that in the theory of graph, you might have a graph which is connected as well as which may not be connected. For example, if I consider this graph,
Sir, I have a question.
yes,
Sir, like, can there be any disconnected graph in which there is no isolated vertex?
any disconnected graph,
In which there is no isolated vertex?
no, that's not possible. So if you have a graph like this, for example, okay, could you please repeat once again?
No, sir, my
So
question was, can
yeah,
we get a disconnected graph in
okay,
which there is no isolated vertex?
let me write. Can we have some disconnected graph then in which
There is no isolated vertex.
Yeah, there is no isolated. Say, consider two disjoint triangles. No isolated vertices. So suppose I have this graph and say this graph. Okay,
Okay.
so
Yes, yes, sir, yes, sir.
yeah, so they are two disconnected graphs, and none of the vertices are isolated. Okay, so it's
Yes, thank
possible.
you.
Yeah. Okay. Uh, yes. So now the question is, so we may have various, for example, this graph along with say this and maybe this. So suppose this is a whole of my graph. Okay. Now you can understand that it has many things like a graph, a subgraph with exactly two vertices, a subgraph with exactly three vertices, and three vertices and a disjoint vertices. Now, what will, how can we describe or how can we justify or how can we develop the theories? So, to develop the theories, we have the concept of components. That means inside any graph, we can always find that graph or we can always break that graph into disjoint components. So what does it mean? Component. For example, suppose you take this. So consider this vertex. Okay, this vertex sets. Okay, so consider this graph. So here, take this vertex and consider all the vertices with this. Say I have, if I name them v1, v2, v3, v4, v5, v6, v7, v8, v9. Okay, so take any vertex. Say I have taken v3. So first take any vertex and consider a set v1 which actually consists of all the vertices which are connected with this v3. That means consider all the paths or consider all the vertices from where to which you can reach from v3. That means what are the vertices? You can go to from v3, you can go to v5, you can go to v6. Okay, no other vertices that you can reach from v3. Now consider any other vertex from v minus v1. Take any vertex, start with that. Say I consider v4, and again try to apply the same idea that from v4 try to reach all possible vertices that you can reach through some path. So you can understand that from v4 you cannot reach to any other vertices. We call it, we called, sorry, not equal to, I take the vertex from here, so I call it v2. Okay, now take any vertex from v minus v1 union v2. Take any vertex from say v1, I consider v1, and try to find all the vertices through which you can move from v1 to other vertices. So you can see that only v1 and v2 are there, and that is known as v3. Okay, now take any vertex from just as usual. So v1 union v2 union v3, and say you can consider say v8. From here you consider v8, and from v8 you can reach to v8, v9, and what is that? Maybe I left with, so maybe v10. Okay, so this may be v10. Okay, now you can see that if there are 10 vertices all over, then the whole vertex set is basically partitioned into disjoint subsets, right? And you can see that each of this v1, v2, v3, and v4, they are maximally connected. You cannot increase any of the vertex inside any of this each of this set, so that you cannot insert any of the extra vertex to keeping the connectivity intact. That means they are maximally connected subgraphs or subsets of V. So you can understand the whole vertex set V having 10 vertices here are actually
Sir, sir,
yes.
hello. Sir,
Yes.
I think, sir, you named V7 as V10 also.
Okay. So maybe then it's V7. Yes, it was 9 vertices. So it's V7. Sorry. Yeah, thank you. So I think it's already there. It's V7. Yes. So what I understand, that the whole vertex set is basically kind of union of disjoint subsets. Now, can somebody be able to tell me when we get some kind of disjoint subsets? So V is there, we get some disjoint subsets. So what actually comes for the first thing that comes to your mind when we talk about that partition into disjoint subsets? When we get, so any hints, any idea?
Sir, when the graph is disconnected.
Okay, when the graph is disconnected, we get this kind of disjoint things. But not asking you the thing. Yes, you are right in that way. But what I am asking in a basic set theoretic notions, like when you have some set and when you get some partitions of
Oh,
this.
equivalence relationship.
Yes, exactly. So if you have some equivalence relation on V, then suddenly you will get a kind of partition. Now, can anybody be able to tell me what could be the equivalence relation that we can define on V so that we might have some kind of partition? Okay, try.
Sir,
Yes.
sir, can the equivalence relation be this that there exists a path between a Vi and Vj are related if and only if.
Okay, say I have V1, V2, say Vk. Okay,
Sir,
now you are defining a equivalence relation rho on V defined by say Vi and Vj such that, what is the definition?
such that there exists a path between Vi and Vj.
Vi and Vj. Okay, let's see. So he has defined a relation. So it suddenly is a subset of V cross V. Now, can somebody be tell me what is a relation on a set, on a non-empty set? What is the definition of a relation on a non-empty set?
So it is a
Say,
subset V cross V.
okay. So a relation is nothing but a subset of, if I consider a relation on a set V, then this a relation is nothing but a subset of V cross V. Now, can somebody be tell me how many relations can we have on a set of V elements? How many relations can we have on a set of V elements? So the question is, so I am also teaching you this counting principle as well. So that's already in our syllabus. So why not now itself? So the question is, how many relations are there on a set of K elements? Somebody, any idea? How many relations are there on a set of K elements? Okay, maybe same question almost. How many maybe symmetric relation, then asymmetric, reflexive relations are there on a set of K elements? Okay, so you just try to think. So I will again come back to graph theory. So first try to see whether the, as Shobnit defined, row. So there is no doubt that this is a subset of V cross V, and by definition any subset of V cross V is a relation on V. Okay, now the question is whether this relation is an equivalence relation or not. The question is rho as defined above is an equivalence relation on V. What is your guess? Is rho an equivalence relation on V? So what would be your answer? Yes or no? So to check whether rho is an equivalence relation, what you need to check actually? Somebody to check. This is okay. Anubhav, will you be able to try? Anubhav, are you there? Okay. Maybe Shubhradeep, are you there? Yeah. Can you tell me?
Yes, sir. Yes, sir. I am present.
Okay. Can you tell me?
Sir, to check whether rho is an equivalent relation, we have to check a rho whether rho is reflexive and symmetric and equivalent
Antisymmetric.
relation to check reflexive, symmetric, and transitive.
Reflexive, symmetric, and transitive. Okay. So tell me whether it is reflexive. So what is the definition
Sir,
of reflex?
reflexive is trivially there is a path between the same vertex. It is trivial.
Okay, good. Symmetric.
And yes, if vi and vj is vi, there exists a path between vi and vj, so symmetrically the this path is between vj and vi.
Very
This
good.
is also
And then
symmetric.
transitive.
Transitive, if there exists a path between vi and vj and vj and vk, then the uh, joining, I mean, the composition of these two paths is again a path, and that would be between vi and vk.
Yes, very good. So that is also transitive. So
Sir,
that implies yes.
sir, I think it would be better. Uh, I don't know. But the thing is that reflect for the reflexive part. Uh, but if there exists a path between vi and vi, it kind of means there exists a self loop, which is not necessary.
No, not necessarily self loop. So if it's a V1, so it's a by convention. So if it's a single point, then that means there is a path from V to V. It not necessarily there is a loop. So by convention, it's a path of zero, length
Mm.
zero.
Okay, okay, sir. Okay.
Okay. So
And
it's not, yeah.
answer for the question, how many relations are there on a set of k elements? Sir,
Yes.
so basically, sir, uh, if say V contains k elements, then V cross V will contain k square elements.
Yes.
Now, now what we have to do is that we have to find the number of subsets of V cross V. Then the
Yes.
number of subsets of V cross V is 2 to the power k square.
Yeah.
And that is the answer.
Yes. Correct. So how many relations are there? So this is the 2 to the power k square. Now, okay, in it's a kind of homework. How many symmetric, how many reflexive relations are there on a set of k elements? You just try to find out this. But yeah, so good. So whatever you did is absolutely correct. So any subset of V cross V is a relation. So there is nothing like you need to find how many subsets of V cross V are there. So each of V consists of k elements. So V cross V consists of k square element. So you are basically trying to find all possible subsets of a set containing k square element. So as you know that the number of subsets of a set having k square element is 2 to the power k square. So that will be the answer. Very good. Now you just need to find these two values. Okay, it may take some time, but it's not that difficult. Okay. So what now we again come back to our business. So what we understand that if G equal to V and E, then we can always define an equivalence relation on V. As a result, V will basically be partitioned into disjoint subsets. Okay. Now tell me what is that each of this partition stands for, or each of this, the equivalence class, not partition, equivalence class stands for. What are they basically? Now you must able to tell me what are these, each of this
The connected
equivalence.
components.
Yes, so they are nothing but the maximal connected components, so they are called components. Okay, each of them are called components. For example, if I have this graph, only this graph, say v1, v2 and v3. Now tell me how many components are there?
Sir,
How
one.
many? One. So you can understand that there is only one equivalence class, because from this vertex you can go any of this vertex. So this is connected. Okay. So this is known as a component. But if I have along with this, if I have this, say v4, v5 and v6, then you can understand that it has two components. So this is one component and this is another component. So this is one component and this is another component. Okay. So this, they are two components. So let me formally define then what is this component. A graph is said to a graph G is said to be connected. We have already done it. Now it's the time for component. It is easy to see that a disconnected graph consists of two or more connected graphs. Each of these connected subgraphs is called a component. The graph consists of, so okay, so they are all done. Okay. Now it's a important result. A graph G is disconnected. A graph G is disconnected if and only if its vertex set V can be partitioned into two non-empty disjoint subsets V1 and V2 such that there exists no edge in G whose one end vertex is in the subset V1 and another and the other in the subset V2. So let me try to explain what is the meaning of this statement. Okay, so you have basically a graph. It says that a graph G is disconnected. So there is a graph V and E, and given that the graph is disconnected, then it says that you can partition V. It says that if and only if, note that this is an if and only if result, if and only if is vertex set V can be partitioned into two non-empty disjoint subsets V1 and V2. So you can partition you can partition V into two disjoint subsets V1 and V2 such that there exists no edge in G whose one end vertex is in the subset V1 and another is in the vertex V2. That means V is actually like this, and if you take, there exists no edge such that, so this is V1 and this is V2, you cannot find any of such edge whose one vertex is from a member of some Vi and another vertex, say, from Vj, which belongs to this. So the statement is quite obvious, right? Can anybody tell me what would be the proof? So first part, say, suppose such a partition exists. So now suppose you have such a partition exists. That means you have V1 and V2, and there exists no such edge. There exists no such edge between. What do you need to show? You need to show that the graph is disconnected. How will you prove that the graph is disconnected? Anybody? Any argument? So that's the formal argument. How to show that the graph is? It's an obvious statement, but you need to prove it formally. The statement is obvious. How to prove the graph is disconnected? What to show that the graph is disconnected? It should have at least two vertices.
Hmm. Yes, sir. Because we can partition it in this way. There exists Vi in V1 and
Yes.
Vj in
So since
V2.
this is non-empty, this is non-empty, there
Yes,
must exist some vertices, say Vi here and Vj here,
such that.
and such
Hmm.
that, and by hypothesis there exists no path between them. So by definition there exist at least two vertices Vi and Vj, uh, between which there exists no path. As a result, the graph is disconnected. So we are done. Now the converse part. So it's an if and only if result. Now it says that uh, G is a disconnected graph. Now you need to show that V can be partitioned into V1 and V2, where V1 and V2 are non-empty subsets, such that no edge from V1 and V2 exist. Okay. Somebody?
Sir,
Yes.
disconnected যেহেতু, if they are
Yes.
disconnected, then we get at least two vertices that are not path connected. And if
Yes.
we take their individual equivalence classes, then these two
Yes.
will be, then if we take union of those two, then it will give us V. Then say V1 and V2 are disconnected, and we take V1's equivalence class and V2's equivalence class, which are respectively V capital V1 and capital V2.
Not necessarily. Your idea is correct, but formal writing may not be the same because it might have three components. So you have taken
Uh,
something from here
mm,
and it might have three components. Then may not be the union will not be V, right?
yes, yes.
Yes, but idea is correct. So now tell me the idea. So that's the logical thinking or logical way of writing. How you are writing or how you are thinking things is very important. Okay, tell me
Yes,
somebody else. Okay, start with any vertex, say V. Okay, from anywhere, say V belongs to V. Now consider the component of V. Since V, given that the G is disconnected, so if you consider the component here and consider this component as V1, okay. So I mean the vertices corresponding to the this component is V1. Since this is disconnected, there must exist some vertex, say U, which is not within V1. Because if U is within V1, then it must be connected, or there must be a path from here to U to V. But since given that G is disconnected, so there must exist some vertex U which is outside V1. Okay. Now take V minus V1. So this is, I call it V2. Can you have any edge? Take any vertex, say from W, from here. Can you have any edge between W and V? Can you have any edge between W and V? If there could be, then W and V will be connected, and in that case, W will suddenly be within the component V1. Since it lies outside this, so there is no edge between V1 and this V2. Is the logic clear to all of you? Any doubt or question? If you have, let me know, please. Is the logic clear to all of you? Okay, Bonani, could you please unmute yourself?
Yes, sir.
Yes. Is the logic clear to you?
Yes, sir.
Good. Okay. So I mean, this is very trivial statement, but sometimes for trivial statement also we need to write something. Now the question is, this is again a very interesting thing. So it says that if a graph, connected or disconnected, it may not, I mean, it may be anything, has exactly two vertices of odd degree. So we know that every graph should have even number of odd degree vertices, but it says that it has exactly two vertices of odd degree. Then, as a conclusion, we have to say that there must be a path joining these two vertices. Again, I am repeating the statement. If a graph, connected or disconnected, has exactly two vertices of odd degree, okay, then there must be a path joining these two vertices. Okay, somebody try to explain. I'll just, yes, statement. So again, okay, I'll just copy this statement that may be easier for you to understand. Okay. I just put it here. I think it's visible now. Okay. So if a graph, connected or disconnected, has exactly two vertices of odd degree, there must be a path joining these two vertices. How to prove this? Somebody may come forward. Okay, somebody. Try to start with something. Okay, let me help. So what it says that it has exactly two vertices of odd degree, right? So what to say something? It has two vertices. Say one vertex is u, and degree of this vertex is 2. Okay. So u is one vertex whose degree is 2, and say another vertex is v, and degree of v is also 2. So they are
Oh,
the
sir,
only.
sir.
Yes, yes.
Oh, sorry. If there exists no path between them, now if we partition the set into connected components, what will happen is that uh, you know
What is two connected components means? Two
oh,
disjoint components.
sorry, to disjoint components, in which in each component uh, every vertex can be reached from another vertex in that component. Okay, sir. Now the problem will happen is that the problem which will happen is that now say there are two vertices of odd degree, Vi and Vj. Now, if there does not exist any path, then Vi and Vj will belong to two separate components. And now what will happen is that, so if we consider those two components, now in that let us choose any one component, and in that component there exists only one vertex of odd degree, which is not
Good.
possible because there has to
Yes.
be an even number of vertices of odd degree.
Very good. So that result is actually we are using the same result many times, right? So what is that result? In it says that result. It says that okay. So it has to be connected graph or in any graph. The result?
So in connected graph, it is trivial that there will be a path.
No, no. What I'm saying, the result, the number
Oh,
of
in any
odd
graph.
degree vertices. Okay. Yes. So in any graph, it says that in any graph, the number of odd degree vertices is even. That means there exist even number of odd degree vertices. What Swapnil explained here is like this. So suppose we assume that there exist exactly two vertices u and v. They are of degree 2. Two vertices of not degree 2. Sorry, I just made a mistake here. So suppose there exist exactly two vertices u and v of odd degree. So their degree is odd. Their degree is odd. Okay. So that means all the remaining vertices, their degree must be even. Now, suppose you consider the first vertex as u. So I consider the component corresponding to u. So the component corresponding to u, say suppose this is say c. C is the component corresponding to u. That means from u, you can go to any vertex within that c. Okay. Now, suppose the other vertex v, which is of odd degree, that lies not within c. If that lies within c, if v is within c, then there must be a path from u to v. So then we are done. So if possible, let v lies outside c. That means v is not within the component of c. Okay. Then in C, you can see that there exists only one vertex whose degree is odd, because there exist in the whole graph, there exist exactly two vertices whose degrees are odd. Remaining all the vertices, they will have the degree even. So within the component C, you can say that there exists only one vertex whose degree is odd, and all the remaining vertex, their degree is even, their degrees are even. Now C, you can consider this as a subgraph, right? So as I mentioned, subgraph is again a graph. So in that graph C, you have only one vertex whose degree is odd. But that should not be possible, because we had already the result in any graph, maybe connected or disconnected, there must be even number of odd degree vertex. But in this subgraph, we have seen that there exists only one vertex u whose degree is odd. That means odd number of odd degree vertices. That is not possible. So this vertex v must be within C. And if that is within C, there must be an edge from u to v. Then we are done. Clear? Is it clear to all of you? Any question? Is the logic clear? So what Swapnil explained, I explained you. Okay, good. So next, let's go to another interesting result. It says a kind of bound. And note that this is true for simple graph, not having parallel edge or self loop. That means you cannot have a graph like this. You cannot have a vertex like this. So this also again an edge. So they are parallel edge. So this graph is not simple, not simple graph. Or this graph is not simple because it has a loop. So this is also not simple. So a simple graph means a graph which has no parallel edge or self loop. Okay. So this statement is quite important. So mind that this is for simple graph. This result is true. For a simple graph with n vertices and k components can have at most n minus k into n minus k plus 1 by 2 edges. So that means you cannot have an arbitrary distribution of number of vertices, number of edges, and number of components. There is a bound. That means there are good relations among these three components or these three parameters n, k, and the number of edges. Okay. Okay. So to make this proof, let us first define a particular kind of graph known as complete graph. Complete graph. So what is the meaning of a complete graph? So what is complete graph? Anybody has any idea? Okay, let me try to explain. So suppose I have given you suppose I have given you two vertices and I ask you draw a simple graph which is maximally connected. Draw a simple graph which is maximally connected with these two vertices. Say this is V1 and V2. So how many edges will be there? That has to be maximally connected, but the problem is I need to have a simple graph. How many edges will you have? With this vertices V1 and V2, it has to be maximally connected. That means this is the only way, right? So if you can also make parallel edges, but as I mentioned, or you can also have a loop. But as I mentioned, I need a simple graph. You cannot allow this. So they are not possible. Now, if I consider three vertices, V1, V2, V3, and if I ask you uh, what could be the maximally connected subgraph? So it has to be like this, right? You might have also like this. Now you'll be able to understand why I call it maximally connected. Sorry, not this. V1, V2, V3. So both G1 and G2 are connected. But which one is more connected according to the definitions or according to your intuition? Which one is more connected? G1 is more connected or G2 is more connected?
Sir,
G1.
more connected means
More connected means I mean intuitively. First try to think intuitively, then some formalism will come.
Said G1.
G1. So because you may say that if you consider in a practical viewpoint, then you can understand that V1 is more connected than this V1 is more connected than this V1, because say for example, if this is a junction, you may come through this side or you may come through this side. But here there is a only one path from V2 to here. So you may not there, if there might be some congestion here, there would be maybe a longer route. Suppose you want to come from V2 to V1, and you found that by some means some congestion is here. So you can deroute the whole thing, and you may go from V1 to V2 to V1 through this path. In that way, you intuitively you can say, but here you won't be able to. There is only one path here. So if some congestion is here, you cannot avoid that congestion because there is no path from here to. There is no alternative path. That means the reachability of the point V1 here is more than the reachability of V2 from some other points, right? Similarly, from V3, if you want to come through V3, you can see that there is only one path here, but here there are two options. You can come here and go there, you can go through this. In that way, intuitively, we say that this is more connected than this one. Now, the intuition is clear. Now, if I say that, see, this is a connected graph, this is also a connected graph. But this connected graph is contained in this connected graph, right? So you have an opportunity to increase this connectivity. But if I ask you the question, can you further increase the connectivity here, keeping in mind that I want some simple graph? Do you have any way to increase the connectivity here? Connectivity in that sense, what I mentioned earlier. Is there any chance to increase the connectivity here, keeping in mind that whatever I will get, it should also be a simple graph?
No, sir, it is not possible.
It's not possible. So it's already achieved a kind of connectivityness. So maximally connected in that sense. Now consider, say, with four vertices, say V1, V2, V3, and V4. Now you may say that, okay, this is a connected graph, this is a connected graph. Again, maybe this is also a connected graph, V1, V2, V3, V4, and maybe keeping in mind the simpleness, you can say that this is also a connected graph, right? So V1, V2, V3, V4. So this is also a connected graph. Now, among this, can you tell me what could be the maximal? So maximal possible connectedness with these four vertices, not this among these three, but I want the maximally connected components or
So
maximally
we can
connected.
draw
Yeah.
six edges. So
Sorry.
we can
Yeah.
draw total six edges for maximal connected graphs. So we can connect for the first we can connect also V1 to V3 and V4 to V2.
Okay. So if I have like this V3 and V4, then basically this as usual, as usual, as usual, and then maybe this.
Yes.
Yes. So you cannot increase the further connectivity of any of the vertices, keeping in mind that the graph, resulting graph should be a simple graph. So that is the maximal possible connectivity that one could have. Okay. Now, actually, this leads to the concept of complete graph. So that's the definition of a complete graph. So now can you tell me what is the definition could be complete graph? What
Sir,
could be?
Sir,
Yes.
sir, for any Vi and Vj,
Yes.
there exists an edge from Vi to Vj.
Very good. So a graph, say a graph G is said to be a complete
also
graph.
if I define it in the way that for a graph with n vertices, if we have n C2 number of edges, that is the complete graph.
Yes. But you have to just add simple graph.
Yes. Yes.
Yes, exactly. I will come to that. From maybe I don't know who told Akash maybe. So Akash told that uh, from take any vertices vi and vj. It has to be vi not equal to vj, so you have to be little more formal. Take any two distinct vertices from G, and if there exists a path between V1 and, so there exists an edge, not path. If there exists an edge between this Vi and Vj, where Vi not equal to Vj, then we called this graph as a complete graph. That means there will always be an edge between any two distinct vertices of that graph. Okay, so that was a definition of a complete graph. Now let us try to what Kolpok told, that I can have a bound. He told that a simple graph with n vertices and n choose two edges is called a complete graph. Right? What you told, right? This one? Kolpok, you told this thing? A simple graph with n
Yes, sir. Yes.
vertices and n to choose two edges is called a complete graph.
Yes.
Now, somebody can explain me what is that? Why Kalpok told the this definition as a complete graph?
Sir, I have a question, sir. A simple
Yes.
graph can be disconnected also.
A simple graph can be disconnected also.
So, sir, if the graph is disconnected with n vertices, then won't it be less than n choose 2?
Then it won't be a complete graph.
Oh, yes, sir. Yes, sir. Okay, sir. N choose 2 because each edge, each vertex is connected to all other vertices.
Yes.
So, like, in how many ways we can choose two, like, like how many edges we can find between in n vertices, choosing two at a time.
Yes.
So that is why it is n choose two edges.
Yes. So basically, you have n vertices, right? So let us try to make it understand with four vertices. So here n equal to 4. Now you need to choose all the edges, right? That means you are taking how many ways, you are basically choosing two vertices at a time out of this four vertices. So there are ways is n choose two ways. For example, how many edges you have? 1, 2, 3, 4, 5, and 6. And 4 choose 2 here. 4 choose 2 is 6. Okay. Any other proof? He has given one proof. Very good. Any other proof that you can have? Any other proof you can think of? So, what is in a complete graph with n vertices? Say V is a vertex of a complete graph. So V is a vertex of a complete graph with n vertices. So what would be the degree of this vertex V? I'm again repeating. Suppose V is a vertex of a complete graph and the number of vertices of that graph is n. So n is the number of vertices of that graph.
Sir, n
What
minus
is,
1.
yes. So degree of any vertex is n minus 1, right? Now how many vertices are there? There are n vertices. And then what is the sum of all the vertices? Sum of all
Two
the
edges.
vertices
2 into total
Sum,
number of edges.
yes, sum of degree of all the vertices. Sum of degree of all the vertices equal to, so each vertex is of degree n minus 1 and there are n such vertices. So n into n minus 1. So let E be the number of edges. So number of edges in G. Then, as we have already proved, sum of the degree of all vertices must be equal to twice the number of edges. So n into n minus 1 must be equal to 2 into E. So E must be equal to n into n minus 1 by 2, and that is nothing but NC2. So there is another way of proving the same thing using the previous result, but Swapnil has given us the proof in an intuitive way, the using the counting argument. So both of them are perfectly okay, and you might have, or you may think the proof in some other way maybe. So that is also possible. So that's basically a good idea to think the same thing in a different way so that you get some idea. Okay, now we come back to our original result. What is states that uh, okay, not here, maybe, yeah, sorry. So the original results says that this one. So it says that if you have a simple graph with n vertices and k components can have at most this many edges. So I'm giving you just the basic idea of this proof. So suppose I have, how many components are there? K components are there. Say C1, C2, Ck. They are the k components of the whole graph. And suppose each of these components, suppose it has n1 vertices, this component has n2 vertices, and this component has nk vertices. Now, given that there are n vertices, now what is the summation in I equal to 1 to k? That is nothing but how much? This is
N.
n. Now consider each of these components C1. Okay. So what is the number of edges in Ci? What could be the maximum number of edges? So maximum number of edges in Ci. Can anybody explain what is the maximum number of edges in Ci? So if I consider this Ei, say consider this, okay, maybe it has, say, number of edges is E1, E2, Ek. What I want to say, Ei should be less than equal to how much?
Sir,
Can anyone?
N1 choose 2.
Exactly. So as you understand C1, so this is a simple graph. So C1, the maximum number of edges. So C1, the maximum thing that could happen, that the complete graph with N1 vertices. Because you cannot go beyond the complete graph. That means you cannot increase the connectivity beyond the complete graph. That means the number of edges that you have cannot go beyond the number of edges of a complete graph with same number of vertices. So you can understand that each of this Ei must be less than the, here the number of vertices is Ni. So Ni choose 2. That means Ni into Ni minus 1 by 2. So in the whole graph, the number of edges, if E is the number of edges, I equal to 1 to k, that should be less than equal to summation I equal to 1 to k Ni into Ni minus 1 by 2. And that can be proved this one. So that is the basic idea how this can be done, and some simple inequality that you need to prove it. So I may give you some, or you can have a look at this book and then you will able to understand what is the idea. It is not very difficult. You just do it. There may be other way to also prove that. So the idea is simple. So that is the point till what I want to mention today. So you just have a look at this proof, and the proof is simple. Next class I will work with Euler graphs, and we'll see that how the Euler graphs plays an important role, or Euler circuit, Euler line, etc. play an important role to solve the Königsberg bridge problem. Okay. So any question if you have, please ask me.